Okay, off we go. So, real quick, I'm starting to hear positive, encouraging signs about the email/server situation. So, fingers crossed. Hopefully, things will be back to normal within a few days. That's not firm; it's just rumors. But anyway, nice to have a little optimism. Okay, so last time we were talking about accumulating quantities. This is an abstraction. That I think is extremely useful. Let me remind you that the purpose of an abstraction is to apply broadly, right? If the only thing you need to describe is one narrow, specific situation, scenario, then be specific, right? And that's a routine way to approach a problem. But if some sort of a structure, if some generality is going to be appearing in multiple contexts in basically the same way, right? But, analogously but different, appropriate to the circumstances. This is when an abstraction is really appropriate. So that's what I've got here, right? So I define this very abstractly, a quantity. Maybe we're talking about mass. Maybe we're talking about work. Maybe we're talking about perimeter. Maybe we're bazillions of different things that we could call a quantity defined on areas, right? And I keep it general so that these ideas will apply broadly. And so, in fact, that's exactly what's going to happen, right? So this idea of an accumulating quantity, or specifically a quantity that accumulates over areas. Namely, when you split the area, the whole is the sum of the parts, right? This idea is going to come up in different situations with different specifics, but in morally equivalent ways, right? So I want to address this as an abstraction, keep it abstract, keep it general, and then we'll just notice as we go along, oh, hey, check it out. Oh my God, it's exactly this scenario. And all the results that we get from thinking about this as an abstraction are free and automatic and instantaneous, right? So it's a really, really valuable idea. Y'all saw this in linear algebra, of course. Why do they define vector spaces in the abstract? And the answer is because there's zillions of them, right? In various different scenarios, various different contexts. And if you prove theorems about them all in the abstract, then you don't have to prove theorems about them individually, one at a time, each in their own little narrow, little myopic, little circumstance. Okay, all right. So we have this idea of an accumulating quantity, and what we saw last time about accumulating quantities is that whenever this happens, whenever the whole is the sum of the parts, like so, right? By the way, don't take it for granted. Doesn't work for perimeter, right? You got to be careful. You got to make sure that your quantity actually is an accumulating quantity. And anyway, when that happens, you can think of the quantity as being distributed over the area, like it's a kind of a stuff. It doesn't mean it physically is. It doesn't mean that you have to think of it that way. It means you may reasonably think of it that way, and this is extremely valuable. So the mere fact of establishing an accumulating quantity, you get to think of it in a nice, physically relatable way that allows you to further think of it with this associated idea of a density. Right? It's a really nice idea, this idea that you've got some sort of a stuff, and you can talk about stuff per unit size. Now, again, not a creepy idea when you're talking about mass. This is so relatable, so been done, right? Y'all have seen that a million times, even back to single variable calculus classes. Stuff per unit size is the thing you multiply by size to get stuff. I mean, again, we've done it a million times, but we can do it as well for much less relatable ideas, like work. Right? We don't think of work as being a physical stuff, as being like a substance, but it behaves like it, so you can treat it like it and think of it like it. So really, really neat idea. And then further, not only does an accumulating quantity behave like stuff and have an associated density, But you can integrate those densities to get integral theorems. So this right here, again, kind of non-obvious. I don't know. What is this density of which we speak? This isn't stuff. What does that even mean, right? Well, we can write that down. We can make sense out of it by analogy, using this idea of it being an accumulating quantity. And strategically, it's not that different from this old boring idea here that y'all have seen a million times. Okay, all right. So, by the way, so likewise in 3 dimensions, same idea. Just, a quantity that accumulates over volumes. Just means that if you split the volume, then the whole is the sum of the parts. It's the same basic idea. And you get all the same goodies. You can think of it as stuff. There's an associated density, and you can create a corresponding integral thing. Okay. Likewise in 1 dimension as well. All right, so we talked about let's see, what page is this? This is page 150. Yeah, so we talked about a specific example of this, and we had to kind of get some definitions on the page. By the way, this is a really important one to make sure that you remember. Henceforth, this word boundary is a loaded word. Right? Part of your job is to remember that this is now a loaded word and subscribes to a convention. It's an arbitrary convention, to be fair, but nevertheless, it's a standard convention. Boundaries are oriented, and they're oriented according to this convention that we talked about last time. So that's again, going forward, whenever you see the word boundary, that's an oriented thing, and it's oriented like so. And with that noted, where we ended last time was this observation that we have a very surprising accumulating quantity, boundary circulation. Weirdly, unexpectedly. That's not a stuff, right? Boundary circulation? That's a formula we write down. It's an integral that we compute. Maybe with fluids in mind or something like that, right? But it's not a substance. It doesn't have units of work. It's not something we ever really thought of before in physics classes or anything. And yet, here we are. It's an accumulating quantity. And so like any other, because it's an accumulating quantity, you can think of it like stuff. It has an associated density which you can integrate to form an integral theorem. And I don't have to think through all of these ideas that we developed about accumulating quantities anymore. That's all free, right? That all applies completely freely because we have an accumulating quantity, because the whole is the sum of the parts because these add up. Thankfully, according to the convention about orientations and how, orientations give you minus signs if you put them the other way, etc. Because it's an accumulating quantity, we just get to instantly say, hey, you know what? That behaves like a physical stuff. I can talk about its corresponding density. I can then compute it as an integral of that density. That's all, boom, snap, instantaneous, free. Right? Because of what we've already shown about this, in the broadly general abstract notion of an accumulating quantity. Free theorem. And here's the theorem. It's called Green's theorem. This accumulating quantity called circulation, by the way, of course, the word circulation does implicitly require that it be a closed curve. So, of course, it's a closed curves or boundaries. So that's all sort of implicit. I like to repeat it sometimes just for emphasis. But circulation is an accumulating quantity. Whole is the sum of the parts. That's what this says, right? And accumulating quantities have associated densities, and so stuff is stuff per unit size times size, and this is what that density ends up being. It's this thing that we call curl. Now, how do I know that curl is the associated density? That's a computation. It's It's a cool computation. It's an important computation, but it's a computation that's a little bit tedious, and ultimately it's just a computation, and it's in the book. If y'all want to look at it, you're welcome to. I would even say I encourage it, but it's not critical. It's not essential that you see how that computation goes down. The most important thing by far is that you understand the role that curl plays. It's the fact that it is the density that is important. It's the fact that I have up here that when I take my accumulating quantity, right? Color mistake. When I take my accumulating quantity of circulation, right? And when I say, hey, what is the associated density that I get for all accumulating quantities, this being 1? And you can just compute. And here's the formula. dq dx minus dp dy. Make sure to know that. It's a very, very, very important formula to have right on the tip of your tongue, ready to roll at a moment's notice. We give it this name. We call it curl. That's one of several names / notations by which it goes. Sometimes it's called rote, R-O-T, short for rotation. We'll talk about why that is in a couple seconds. Likewise, the word curl kind of conjures to the mind. It kind of conjures a similar image of, this kind of thing. We'll talk about why again in just a minute. It's just the density of this accumulating quantity called circulation. By the way, a couple other notations you should be aware of. This one right here is interesting. Del wedge F. Y'all remember the wedge product from back in chapter 1? I guess it was late chapter 1. Yeah, it's in the section on like cross products and determinants. And I, at the end, mentioned this thing called wedge product. It's kind of a two-dimensional. It's not the same as cross product, but it's similar in certain ways. It has some of the same properties, right? So anyway, wedge happens to be, if you just write down del wedge F, it just happens to be exactly this formula. It's kind of handy. So some people like this notation. At some point, this is a little bit of a me story. I have always been a little uncomfortable with calling this curl, and it's because there's another curl that we're going to see later in the course, and it just kind of a little bit of a nails on a chalkboard thing to me to call two different things by the same name. It just bugged me, and so I was wanting to find a different name, and so it occurred to me this is the operator inside of the theorem universally known as Green's theorem, so why don't we call it Green's operator, and I abbreviated that as GRN. The only reason I'm showing you this at this point is because if you look through my old exams, my old midterm exams, which I hope and assume that you will, you'll see GRN various places. And I just realized that's just that was a harebrained scheme that I had 15 years ago, and finally decided to abandon maybe a couple years ago. Anyway, heads up. You probably won't see that anywhere else. And then in the book, they in at least one place they've written down this notation, and I am going to put a little bit of an X through this because it's really unfortunate. To take a two-dimensional vector field and then to start throwing around cross product. Cross product does not work in 2 dimensions. It doesn't. Right? It just doesn't. It's a 3-dimensional thing. As a binary operation, cross products in 3 dimensions. We have here a vector field in 2 dimensions. That doesn't make sense. That only kinda vaguely makes sense if you just sort of assume a comma 0 at the end, which you shouldn't do. That changes the critter from a 2-dimensional vector field to a 3-dimensional vector field. It's not the same. So anyway, that bugs me, but it's I've seen it elsewhere. So again, sort of a heads up. Okay, so again, all of that is just terminology and notation for what I strongly hope that y'all will think of in your mind in this sense right here. It's the associated density for this accumulating quantity called circulation. And being as it is that density, right? That's the density in this integral theorem. And so if you want to compute circulation, you do so as an integral of that density. Let me pause for a second. I know I've been expounding a lot here. Does anybody have any questions? We've got examples coming up, of course. Yes?
Could you explain the bounds on the integral, on the how it changes?
Yeah. That's right. So that is a weird thing about this theorem. In fact, let me clean up the mess. Talk about that a little bit. It's a great question. So this integral is on the boundary. This integral is on the interior, right? And I hope this didn't sneak past some of y'all. Perhaps that little notation there that looks like a partial derivative symbol means boundary. Does that help? Okay, all right. Yeah, maybe that's okay. Cool. So that is going to be an important point. It's going to come up as part of my next example. But yeah, nevertheless, it's important to realize that the domains are different. That's one of the cool things about this theorem. And of course, it kind of comes up naturally because we start off literally by thinking about boundary circulation. That's the integral we start off with. That is our accumulating quantity, so the domain, of course, is the boundary. But it accumulates over area, because that's the accumulation feature that we describe, is that when you cut the area into pieces, and so the resulting summation is over the area, and thus the interior. Yeah. Okay. Weird feature. Okay, now before I show you the next example, I do want to talk about, why does it kind of make sense that we call it by these names, curl and rot. What is the rotational aspect of what we're talking about here? And let's just go back up to what it is, right? Curl. Well, let's see here. Curl, aka rot, aka all this other stuff, is circulation density. It's circulation per unit area. Now let's think through what that is. What is circulation as relates to this picture? Circulation says on each little piece here in particular that we're going to compute line integral around these boundaries. Right? That's the first thing we'll do, is talk about the sum of those four line integrals, or the line integral around that boundary curve. What's that? Just a rhetorical question. Let's remind ourselves. Circulation says, well, it's a vector line integral. Vector line integrals say to what extent is the fluid flowing along the curve. This curve is going around in a kind of like a circle, right? So circulation is literally measuring the extent to which the fluid is kind of going around in a circle, and thus I think the term circulation is actually pretty plausible. So circulation density means, of course, that we're going to divide by the size. So we have circulation per unit area. And altogether then, circulation that we're looking at measures to what extent is there kind of a rotational aspect in the fluid. Viewing that as the corresponding density by dividing by area means, in some sense, we're trying to figure out, this is trying to represent to what extent at a given point is the fluid kind of rotating, is the fluid kind of turning at that point. Right? Or you might say that it's like, the term curl, not really quite the correct conjuring in my mind, but curl is supposed to suggest something that's like this, like maybe as if the flow lines maybe curve or something like that, which of course isn't really the right point. Anyway, that's the rotational story. That's why we think of curl in this way. Curl represents how the fluid is rotating. Okay, examples. Let's do it. Here we go. First example. We've got here a curve. clockwise oriented unit circle. And around that curve, we want to compute the line integral of this vector field, F. Vector line integral, oh wait, it's a closed curve, so this is a circulation. And we think to ourselves, okay, we want to compute a circulation. We've got a brand new theorem about circulations. Seems like we're in business. Seems like we should just be able to apply this theorem. There is a sticky wicket. You do have to be careful about this. Easy landmine to step on. Please don't step on it. Here's the sticky wicket. Notice right here, it says that your circulation, if you want to use this theorem, your circulation has to be around a boundary. Further reminder, boundary, loaded word. Loaded, right? Boundary means oriented according to a very specific convention. So we have to ask ourselves, we have to come back to this picture and ask ourselves, hey, wait a minute. Is this curve, let's see here, is this curve a boundary? Does this follow the prescribed convention? And sadly, no, it doesn't. It's going the wrong way. Does everybody see that? It just doesn't follow the rules. This is not a boundary. As I move, as this curve is oriented, the region is not on my left. The region's on my right. Okay, so sadly, we cannot apply Green's theorem yet. This Green's theorem only applies to boundaries and, orientation in mind. This isn't. Okay, so here's the workaround. Now, that's where the landmine is. Now you know not to step on the landmine. Let me show you how to bypass the landmine. You bypass the landmine by realizing that this curve, it's pretty much if we ignore that orientation stuff, it's a boundary. The only thing that's wrong is the orientation. If I were to just orient it the other way, right, that resulting curve, differing only by being oriented the other way, is a boundary. Strictly. According to the conventions and everything. All good. Right? So, other than that minus sign that results from orienting the other way, yeah, it's totally a boundary. Go ahead. Right? So, the way I recognize this is by recognizing that the curve we were given and the curve that actually is a boundary differ only by orientation, and thus I get a minus sign. Everybody see what I did there? It's a nice little slick move, right? A little side step over the landmine of orientation. By the way, orientation's a big deal. It really is. It's an enormous deal. The theorem only works because of conventions we chose about orientation. You only get accumulation because of the cancellation in that shared interior edge piece. Right? That cancellation only happens because we agreed to solemnly follow conventions according to orientation. So it's a really, really big deal. Just for the record, I'm fully aware that, but the only thing that it does is give you a minus sign, everything, it's a sign error, arguably, right? But there are different kinds of sign errors, and please be very clear about this. The kind of sign error that we all make because we're human and fallible, there were 3 minus signs, and somehow we canceled all 3 of them and got minus cubed. It was plus. Okay, that kind of nonsense. We're all susceptible to that silliness, and that's just silliness, of course. No problem. That's not what this is, right? This is a minus sign that is a consequence of a deep and significant idea, substantial, meaningful, deep, significant idea in the course. And getting this wrong is not a brain stumble triviality. Getting this wrong is representative of misunderstanding a serious, significant part of the course. Right? So heads up, I'm just, don't say I didn't warn you. On exams, orientation errors and sign errors that result from orientation misunderstandings are worth significant points, right? Like, so on a 20-point question, if this were a 20-point question, getting the orientation wrong, ballpark, I'd probably count off about 4 points. It's a big deal, right? It is, again, as far as the concepts that we're interested in confirming that you understand by a question like this. Orientation is a significant part of what we want you to understand. So I hope that makes sense. Anybody, any questions about that? Everybody's clear on the... Yeah?
How did you compute the integral?
Oh, I haven't gotten to that yet. Yeah, I'll get to that in a second. Yeah, totally. But about the orientation business, is everybody clear on the take there? Okay. So yeah, moving along. Yeah, so natural next question, how do we actually compute this integral, right? We've gotten it down to, I know how to deal with minus signs, so I really just at this point need to figure out how to compute that integral. And how do I compute that integral? Well, conveniently now, this is a boundary. Green's theorem tells me that when I have a circulation around a boundary, boom, I can just write it as a double integral of curl. Double integral of circulation density. And just write it down. And that's this next step that I've done here. We've got a circulation around a boundary, and boom, double integral of curl. So that's where we invoke the big gun, right? In this example, Green's theorem is the big gun that does the heavy lifting for us. And so now of course, don't forget your minus sign, right? That minus sign carries along. Well, of course it does. It's algebra. Okay, so how do I compute curl? Well, we have a formula for it. Going back to here. Curl, aka circulation density, is computed by this formula. And notice I'm going to take the second coordinate of my vector field, take its x partial, and then I'm going to take the first coordinate of my vector field and subtract its y partial. Okay. So, cool, no worries. We do that here. Curl, taking taking this vector field, computing its curl, a little bit of easy partial derivatives, you end up with very conveniently just 2, which is awesome. We got lucky. You won't always get that lucky, of course. I manufactured this example as a part of my sales pitch. I want you all to like Green's theorem. I want you to see how awesome it can be in some cases. And this is fairly routine, right? I mean, cool algebraic good fortune like this is not rare. It happens on the regular, right? So, it turns out to be 2. We have a double integral of 2 over a garden variety geometric shape. Don't forget, of course, we have passed now to a double integral over the thing whose boundary we're talking about, right? And that integral is, like I say, easy to compute. And the nice punchline is that our circulation is minus 2 pi. How we doing? Everybody see the process here? Okay. All right, so it's a pretty awesome theorem. By the way, let's real quick just recognize what we saved ourselves by this method. I mean, if I had done this the old-fashioned way, if I had parametrized the curve, right, I mean, no problem. I can parametrize that curve, but x and y are going to be like sine and cosine, which means all of this is going to be sines and cosines. I'm particularly scared of having to figure out how to do an integral where tangent of cosine of t is part of my integrand. That just looks creepy and weird and highly undesirable. I think that would be a very undesirable integral to have to do the old-fashioned way. Right? So, using the big gun, using Green's theorem saved us loads of inconvenience. Okay, here's another example. This one's a little bit trickier. Here, our path is made up of various line segments, like so. And that's the path over which we want to do a circulation. And now let's ask the question, as I follow the directions given in this, as this curve is described, is the region on my left? Well, over here, as I go as prescribed, yes, the region is on my left. But, over here, it isn't. Over here, the region is not on my left. The region is on my right. All right, so we have a problem here. The orientation of this curve that I have is not as a boundary yet. So here's the slick move. The clever idea is to take this path oriented as indicated and rewrite it as this, which is a boundary, and then plus this that I have here in orange, which, okay, well, there's not a boundary. The orientation's wrong. Oh, man. If I say it's the boundary of D2, I'm wrong because of the orientation. But what I can say is that it is just literally that boundary oriented the opposite way. That's exactly what this orange curve is. If you take the boundary of D2, you will get exactly that orange curve, but go in the other way. So we recognize with that, again, our new notation from a couple days ago, that superscript minus sign. That just says orient the other way. Everybody see what I did there? It's a slick move. Okay, so that being said, okay, now all together then, the actual curve that I was given, this total curve is, well, let's see here. It's that blue curve plus this orange curve. And that orange curve, keep in mind, is just an opposite orientation on the boundary of D2. So you just pop that little minus sign out. Again, that's what orientations do. If you switch the orientation, you get a minus sign. So cool, you recognize that there. And then notice, now what we have is just a couple of different boundary circulations. And yes, one of them is oriented the wrong way, right? This one is oriented the wrong way, and I've already accounted for that with that minus sign. And so, again, once you've got it recognized as boundary circulations, Green's theorem, right? There's the big gun. Don't forget to compute curl. Oh, whoopsie. Don't forget to compute curl. Now, again, this is just algebra from what you're given. And this vector field that we were given up here, if you compute its curl, right, the curl of this vector field, it ends up being 9. No big deal. Now that leaves us with a couple of integrals. Integrals, again, of constants. Gotta love it. And conveniently, they're integrals of the same constant over regions with the same area, and so the difference is just 0. And so again, we saved ourselves loads of trouble. Easy integral, as opposed to 4 separate parametrized pullback, lots of details, lots of opportunities for careless errors, lots of tedium to go through. Much more difficult calculation to do it without Green's theorem. Everybody all right? Okay, so these are, we're getting into we're getting into the good stuff. Chapter 6 and 7 is where stuff gets really exciting. Green's theorem is the first of these big, exciting theorems. The way we're doing it in this course anyway. And this is neato stuff. It's almost like a magic trick. Right? I mean, it's just mysterious how, we were talking about a line integral, and then all of a sudden, we wave the magic wand and say the magic word, and all of a sudden, no, it's a double integral. shocking. Okay. All right. Now, here's a nice application. This is cute. It's just a special case of Green's theorem, and I'm going to justify this conclusion by starting in the middle. And what you're going to notice is that this equation I have in the middle here is literally just exactly Green's theorem, right? Line integral over a boundary equals double integral of curl over the interior. It's straight up, no asterisk, Green's theorem, as is applied in this case to this specific vector field, 0, x. Now, why did I choose 0, x? Side note, there are various different options you can put here and you get an analogous result. This is my favorite not quite arbitrary, my favorite of the many choices that we have here to use 0, x because it's the simplest one. I've never seen a simpler one than this. And so this is one I like to use. Anyway, that said, what's great about this particular vector field is that when you look at its curl, it's exactly 1. That's kind of neato, right? And in particular, the value of it being exactly 1 is that now, check it out, I'm interested in computing a double integral of 1, and of course that is just area. You're literally adding up a bunch of little pieces of area that gives you, of course, then the whole total area. So a weird result, and let's just clean up the mess here, a circulation around a region will allow you to compute the area inside of that region. It's one of these unexpected things. Like if you're interested in computing an area, which is an intrinsically two-dimensional calculation, here we have a one-dimensional calculation that will do it for you. And sometimes that ends up being extremely convenient. Okay, now before I go on, I'm just going to write down a notational, this is optional, but it is actually pretty convenient here. Y'all remember this idea of coordinate line integral notation. I went through that pretty quickly. Give me 2 seconds. It's just an alternative notation. If you write down dr as dx comma dy, and then you literally write out that dot product, then this is all you get. You just get x dy, and you sort of see how the algebra on that works out. Again, in most circumstances, I don't really like the coordinate line integral notation. It tends to be clunkier, right? And in most cases, it doesn't offer an advantage. But I think I will agree that in this case, what I have on the left is more compact. So most of the time, when you see this theorem, most of the time you'll see it like this, just because it's more compact to write. And just remember, all that is an alternative notation for a circulation giving you an area. Yes?
Could you compare this integral that you're doing here with the one above and why this one gets area and that one something else?
Oh, yeah. Because here I chose to use a very special vector field, special because it has this feature that curl is exactly 1. Yeah. Now up here, in this example, notice I have a different vector field, curl isn't 1. And over here, I have, again, a different vector field and curl isn't 1. And that's why you don't get the area.
So it's just like one special case where it equals the area where it normally wouldn't?
Yeah, I mean, if you take a generic vector field, right, for a generic vector field, curl is a formula, right? And who knows what that'll end up being? It probably won't even be a constant, right? So yeah, finding a vector field where the curl is exactly and always 1 is that's the trick that makes this all come together. Is that cool? Yeah. All right. Okay, so now you may be thinking to yourselves, you know what, this integral is kind of a pain to compute also, and I've been computing areas since I was in middle school geometry class, and so thanks but no thanks. I'm just going to stick with high school geometry. You may be thinking that. Sometimes that's a fair choice. But let me point out, this integral can be really easy to compute in some cases. Now, that's not the same integral as this integral. These are different. top integral is over a boundary. Domain is a boundary. This blue integral at the bottom is not over a boundary. It's over a line segment. So totally different in that sense, right? But what's awesome about this blue integral is it's really easy to compute. And by the way, this is a good exercise. I think everybody should crank this out. It'll take you 5 minutes. It's not that big a deal, and it's a healthy exercise to make sure that you it'll check some various different things for you. Do you have a proper understanding of coordinate line integral notation? Do you know how to parameterize a line segment? Good thing to know. Do you know how to carry through the integration? Okay, so good exercise. I hope you give it a try. Notice how nice the answer is. The average value of x times the change in y. It's super easy to just at a glance compute. Yeah.
In application,
yeah.
Taking like the integral over boundary.
Yep.
Because it's a closed loop.
Mm-hmm.
Would the like dr and like would we necessarily have to be like trigonometric I guess terms to have even able to do a closed loop to go from 0 to 2 pi, for example?
If it's a circle, but in general, the point is you have to parameterize the curve. And every curve is different. You're going to get a different parameterizations, and it won't always have trig in it, right? It could be a polygon, in which case there's no trig. You just have to parameterize appropriate to the curve.
I guess just what I mean then is with the parameterization, you can get to the same point at 2 different values of t.
Yes.
Okay.
Yeah, that's right, because it has to be a closed curve. Okay. If you want to talk about a boundary line integral, it's always going to be a closed curve. Absolutely. Yep. Okay, so let's look at this scenario here. I want to compute this area, and now, again, if you just want to stick to your guns and do this with high school geometry or middle school geometry, whatever, look, I guess you could, but yikes. Can we recognize that's, if I break this up into pieces by, I can cut this, for example, into a bunch of triangles, which I believe is 7 triangles. And here's the problem. Most of those triangles are not right triangles. And even if maybe 1 or 2 of these were a right triangle, certainly in general, they need not be right triangles. So generically, you would expect this kind of thing to break up into non-right triangles. How do you compute the area of a totally irregular triangle? It's not that convenient. Right? That's a pain. It's a real pain. I don't know, do not recommend. So here's how we're going to use the big theorem up here. We're going to compute this boundary line integral. I'm going to go all the way around that boundary like that, oriented, of course, in the correct direction, right? How am I going to compute that boundary line integral? Well, I'm going to recognize that one piece at a time, we're talking about line integrals on line segments. And line integrals on line segments are super, super easy to compute. Each one of those line segments, it's got a starting point and an ending point. I can see right from the picture what those coordinates are. So, for example, on this first line segment, what's the average value of x? Well, we're starting at 1, we're ending at 12, and the average of those is 6.5. Right? Nothing to it. What's the change in y? How much did y increase? Well, y went from 1 to 6, so delta y is 5. And by the theorem that we wrote down up here, on a line segment, you multiply, that gives you the line integral. So on each one of those lines, you can carry this around. Do this on all 9. I've got the arithmetic here if you want to see how that carries through. But you just go around all 9 of the edges here, and a little arithmetic. No big deal. It doesn't even have annoying fractions in it, right? It's just pretty straightforward. And punch up the arithmetic, and that will give you the total area, which apparently ends up being 19. Right? So imagine, again, the nightmares of having to do this the old-fashioned way, having to drop perpendiculars to compute the corresponding heights. Every edge length like the base of each one of those triangles, if you do this the old-fashioned way, it's going to have square roots in it. Somehow, all of which are going to cancel because the answer is 19. But if you do it that way, you're going to deal with square roots. Highly undesirable. Major bummer. And this bypasses all of that. It's a pretty cool little application of Green's theorem. Great thing to know about. By the way, just for fun, I'll interject. One time it was shortly after 9/11. There was a lot being said about the plot of the World Trade Center. Right? And the New York Times was writing an article about it at some point in, I don't know, 2002 or 2003, somewhere along in there. And they had survey data on the plot. And by the way, the plot is not a rectangle. The plot is a multi-sided polygon that doesn't have right angles. It's not this weird, but it's analogous. Right? And so the reporter had this survey data and was like, okay, well, here's some angles and some distances, and I don't know how to compute the area of this thing. So the reporter called up Columbia University and said, I have a geometry problem. And Columbia University said, okay, well, we have a geometer, on the premises, and it turns out my brother was the geometer. That was now the funny part, of course, of that is he was not an expert in high school geometry. He's an expert in differential geometry. It's a very different thing, very sophisticated stuff. But anyway, so they called him up and said, can you compute this area for us? We don't know how to compute this area. He did exactly this calculation, and as a result got cited in the New York Times. Right? I thought that was kind of cool. So, anyway. All right. Moving along. So, flux. Y'all probably remember flux from chapter 3, I guess it is. 3.3, I think it is. Anyway, flux is an idea we talked about, and we talked about it in the context of 3 dimensions. So you have a 3-dimensional fluid like the air in this room, for example, and maybe I've got a screen and I want to know how the air is moving through that screen. Or I think another metaphor that I used at the time was, imagine you have water flowing around, let's say in the ocean, and you throw a net out there, right? And the water is flowing through your net. You want to know how many fish you're going to catch, and you'd like to know the volume per unit time of water flowing through your net. And we do this with a calculation called flux. And we actually wrote that down back in chapter 3, and I did a calculation where we talked about volume per unit time, and we make the little parallelepiped of volume of water going through our little region, and carried through some details. All that's different about what you see here is that it's 2-dimensional instead of 3. Right? So here we imagine a 2-dimensional fluid. So for example, maybe you have surface water that's flowing around on a concrete slab, or maybe on the surface of the earth, and water is flowing around. I like the metaphor of migration of like herd animals, right? Which are a kind of a fluid in a way, sort of, right? And so likewise, you might ask, for example, if I know a formula describing how the zebras are migrating, and if I have a line, maybe that's part of a national boundary or something, or the boundary of a national park or some sort of reserve or something like that, you'd like to know, perhaps, yeah, okay, but how many zebras per unit time are crossing into the reserve or out of the reserve or what have you. Right? So quantity per unit time of fluid flow given the velocity or density times velocity, or whatever, however you set up. And again, it's different in every circumstance. So that's the idea of flux again, and it's computed by a very similar formula. Now this too is an exercise that y'all can totally do yourselves, and I think this is a very healthy exercise. The way you're going to do this is you're going to go back to chapter 3 and see how we did it in 3 dimensions, and then you're going to do the morally equivalent, same basic idea here in 2 dimensions. So instead of computing a volume of fluid that's passed through an area, you're going to compute an area of fluid that has passed through a curve. And so let's see here. So for example, given this fluid flow, well, after a certain amount of time, there's the parallelogram that represents fluid, now area not volume of fluid that has passed through our curve. And you just compute that. Again, shamelessly copy, just cheat off of the calculation we did back in chapter 3, right? And what you're going to find is that the answer, hopefully no surprise, looks pretty similar. It's kind of the same sort of idea. Right? So we're going to care about not the vector field exactly, but the extent to which the vector field is pointing in that normal direction, right? So I'm going to want to know how fast in the normal direction is the fluid flowing across the curve, and then we're going to multiply that times the length of the curve. So I hope that seems kind of plausible. Again, excellent little computation for y'all to do on your own. Good little comprehension check. With that, we're going to now consider a harder problem. We're going to consider what if you have not just a line segment, but a curve, but even worse, what if your curve is a boundary of some region, right? And so maybe I've got a scenario kind of like this, and there's fluid flowing along, and I want to know, but all together, to what extent is the fluid flowing through this boundary? And now, of course, we do have to specify a direction, right? The way we specify the direction is what we call a normal vector, right? This is an orientation unit normal vector, and it's the convention. And again, whenever you say boundary, there are conventions. They are arbitrary. They were arbitrary. Now they're standards, right? So anyway, kind of arbitrary, but also standard and therefore fixed. Conventions as to which direction is the orientation on said boundary. And the convention in this scenario wasn't up to me. This happened hundreds of years before I was born. Convention is outward. That's the convention. Right, so for example, as the fluid flows, here's the fluid flowing, and you can see maybe along in here, there is clearly a positive outward flow, right? But that same flow is inward over there, which, given the convention that outward means positive, down here we're talking about a negative outward flow because it's inward, it's not outward, right? So altogether, if you add up over this whole boundary, how do you compute the total amount of flux? In other words, grand total, how many zebras per unit time am I losing out of this reserve? Right? And keep in mind, that's what flux represents, is stuff per unit time passing through the boundary, aka leaving. Okay. All right, so, let's start doing it. By the way, for the moment, ignore all of this. We will come back to that in a bit. For the moment, we're going to take our curve, chop our curve up into little pieces. Let's see, I think I'll do it like this. On each little piece of curve, such as this little piece of curve right here, for example. I didn't mean to do that. Sorry. On that little purple piece of curve, it's approximately a line segment, isn't it? And on a line segment where the vector, by the way, it's also a little bitty line segment, which means those points are all close to each other, means the vector field's approximately constant. And so on that little piece, it's really easy to say, just using the formula on the previous page that y'all are going to derive for yourselves, F dot n times length, and the length of that little piece of curve is ds. So we just write that down, super easy. Right? And then, of course, I want to add up over the entire curve to get the total flux. So that first part, no big deal. The big problem is trying to figure out how do I compute an integral like this? Where have we previously computed integrals like this? And answer, we haven't. We haven't seen integrals like this before. We don't know what to do with n ds. Never seen it before. So what do we do? And here's the slick move. A very clever little two-step here. The big idea is to notice that f dot n, the dot product of these two vectors, is unaffected by rotating both vectors 90 degrees counterclockwise. The dot product doesn't change. The vectors obviously change, but the dot product doesn't change because dot products are computed in terms of magnitudes, which don't change when you rotate, and the angle between. And now again, geometric appeal, if you have two vectors and if you rotate them the same amount, the angle between them doesn't change at all. Right? Does everybody see that? Right? So this is a slick move, but you can totally rotate both of the vectors, and this orange dot, try to do better. This orange dot product that we're interested in, well, it's going to be the same as this dark blue dot product that those vectors rotate into. And hopefully y'all remember how to do 90-degree rotations. By the way, it's it's in the prerequisite trail of this course, right? So linear algebra is a prereq, so make sure that you're good with using linear algebra to do stuff like rotating vectors. Rotations are linear transformations. Linear transformations are represented by matrices. Matrices are understood by columns, and columns are images of standard basis vectors, right? So that's a powerful geometric interpretation of linear transformations that we're going to be doing a lot of in this class, and that you'll see plenty of outside of this class. So make sure you're good with that. Reminder, if you're not good with it, come talk to me, right? Office hours. Happy to help. No problem. Right? We'll take all the time you need to work out those details, but make sure you can do that. Okay, so as noted here, by way of this 90-degree rotation argument, I can rewrite that integral like that, and this is something we know how to deal with. No problem. I know how to deal with TDS. That's dr. I know how to deal with integrals dot dr, vector field dot. That's just a vector line integral. That's our old friend. All good. And in particular, in this case, the way we're going to deal with this vector line integral, we're going to notice it's a boundary vector line integral. Boundary circulations, aka, right, are computed as a double integral of curl. And curl is not hard to compute. It's a matter of writing it down. Now, there's one little hiccup on this. Don't make the mistake of writing down curl as just dq dx minus dp dy. The formula is not dependent on the alphabet, right? It's about which coordinates are in which positions of the vector field. So you'll recall when I first wrote down the formula for curl, here it is, right? Curl, aka circulation density, this thing, right? I emphasized that it's the x partial of the second field coordinate minus the y partial of the first field coordinate. And in this example here, we are looking at f perp, right? The result of having rotated f, not f, the result of having rotated f. And so with this in mind, let's see here, x partial of the second coordinate, that second coordinate is p, minus then the y partial of the first coordinate, and that first coordinate is minus q. Is everybody good with that? Yes.
In physics, we have done it with just like the second integral and like didn't do any of this changing
Yeah,
and stuff. So like, what's the benefit of doing it this way?
Yeah, it's just an it's a tool for your toolbox. Yeah. So I mean, sometimes. So y'all have heard me say this a million times that, tools for your toolbox. Sometimes this integral right here, sometimes you get geometrically lucky. What if this dot product is like obviously 0? Yeah, then you don't need to do all this stuff, right? Or it might be convenient to deal with for other reasons, given the context. Sure, right? But in a lot of cases, this tool is a pretty neat tool because we're not quite done developing it yet, but you can see the punchline is going to be that we can compute flux with a double integral, and sometimes that's a lot easier, depending on the specifics. Yep. Okay, so go ahead.
Why is you said TDS equals the R? Why?
What? The what now?
TDS.
Oh yeah, this goes back to. Let's see. When would that have been? We started it in chapter 3. I defined the dr vector and the t and related the t to the velocity and the velocity to the length, and there was just a bunch of players that all kind of relate in different ways. It's the very start of I think it's section 3.2, and you can look back in the notes to that, the very top of section 3. I think it's 3.2, and then we revisited this stuff again when we first started defining vector line integrals. So it's just it's a standard formula that we've used at several points in the past. Yeah.
Why do we have the extra negative sign within the partials formula?
It depends on what you're taking the curl of, right? So here I'm taking the curl of f perp, and it's because of that again it's about the what are the coordinates of the vector field you're taking the curl of. Yeah. Cool. Okay, so we're basically there at this point. Not hard to persuade yourself that these minus signs cancel. And then that integrand turns into this, which we recognize as something we've seen previously called divergence, which we denoted like that. Again, flashbacks to chapter 3. And there you go. We've got ourselves a new big gun theorem called the two-dimensional divergence theorem. So this is it's basically a spin-off of Green's theorem, right? Of course, we used Green's theorem as a main part of our argument here. That's what passed us from line integrals to double integrals. But this is a totally different result because it's not about circulation. It's about outward-oriented boundary flux, right? And the answer isn't a double integral of curl. It's a double integral of divergence. It's a different result. But it's kind of a twist on Green's theorem. All right. Okay. Example incoming. But before we do that, I want to talk about this notational little sidebar over here, this little alternative thing. Turns out you can rewrite that like this. Now again, if you like the wedge, right? And I, have to acknowledge that wedge makes for a more compact notation there, doesn't it? Right? Now I think it's less common. I've seen this quite a bit less than I've seen the dot product notation. But it's, you are going to see that wedge notation. And by the way, it is officially part of the course, and so you are required to be familiar with that notation. It's stuff you have to know. Now, why does this work? This results from an easily checked little bit of algebra, and so make sure you can do this. Make sure you can confirm. Now, this is for two-dimensional vectors only, but a dot product is a wedge product with a rotated second vector. That B perp just says rotate B counterclockwise by 90 degrees. And so ultimately a wedge product kind of is a dot product and vice versa. You just have to rotate one of the vectors. And when you apply that to this, right, and what happens when you rotate in 90 degrees counterclockwise? Well, it rotates to become T. And again, geometric appeal, right? You can see it right here. There's your N. And when you rotate 90 degrees counterclockwise, check it out, it becomes T. So it just kind of works out kind of nicely like this. And, of course, TDS is DR, and thus the wedge DR right there. So, like I say, alternative notation. Okay, let's see an example. Here is a question. Here's a computation we want to do. It says we want to compute flux. By the way, when you have when the orientation is not specified, it is understood that the word boundary isn't used in this example, but just don't forget, in general, when you see the word boundary in reference to flux, that means outward oriented. That's the standard convention. Here I specifically say it, that this curve is oriented outward through the unit circle. Okay. So, again, look, you can, I suppose, compute this brute force. You can plug and chug it. You parameterize the curve, write down the formula for the normal vector. It's total pain, right? You really don't want to have to do that. So I'm going to put a frowny face on that. Much easier is to use our big gun theorem, right? So the big theorem that we just wrote down is that if you want to compute flux, it's a double integral of divergence. Let the theorem do the heavy lifting for you, right? That's the power of this theorem. And the divergence is easy to compute. So for this vector field, you compute the divergence. Ends up being pretty easy arithmetic, and the divergence ends up being -3. And, again, constant. Gotta love it. And not rare to end up with really nice results about, divergence working out to be much prettier than the vector field whose divergence they represent. Okay, so not a rare scenario, and this ends up being, of course, a super easy integral to compute because this is a constant, and our region is the unit disk. Nothing to it. The integral's -3 pi. Everybody good? Okay, so again, neat result. We like it. This, let's see here, what we call the two-dimensional divergence theorem is like so. And notice that how we proved this, though. Green's theorem did most of the work. Right? Green's theorem was the thing that, I was playing around with notation before that, and then I was kind of playing around with notation after that. But Green's theorem was what did the lion's share of the effort in making this happen. So you can think of this as being a spin-off of Green's theorem. Now, the next thing I'm going to point out is that there is a totally different way to think of this theorem. Totally different. Arguably better. Here, we kind of have to relate to Green's theorem. Again, Green's theorem did our work for us. But check this out. You say you're interested in boundary flux. Rather than rewriting boundary flux in terms of circulation, notice boundary flux is also an accumulating quantity. And once you know that, now we'll talk about why in just a moment, right? But once you have that boundary flux is an accumulating quantity, we know stuff about accumulating quantities. Accumulating quantities, they behave kind of like stuff. You can talk about the associated density, and the whole is the sum of the parts, meaning that you can just integrate that density to get your result. Right? All of that is free once you realize you have an accumulating quantity. And so I'm just going to make this assertion. Boundary flux is an accumulating quantity. And here's how you see it. For this left side, there's my outward-oriented boundary flux, oriented like so. Okay. For this right side, here's my outward-oriented boundary flux, oriented as indicated, right? Again, outward from the thing whose boundary you're talking about. So for D2, that's what outward is. And is the whole the sum of the parts? Well, again, everything looks good except for this stuff in the middle. There's our discrepancy. This is what we have to be concerned about. But notice, this again, kind of geometrically different. But again, we're talking about a single shared edge that we're integrating twice with opposite orientations, which then cancel. Now, okay. Gosh, that sounds familiar, right? I mean, we've previously, by the way, I deliberately drew the diagram and I deliberately copy-pasted the text to look just like I wrote it down when we were talking about circulations, because I want that analogy to be as blatant as possible. It's morally equivalent. It's just that now, since we're talking about flux, we're talking about opposite directions through the curve. When we were doing circulation, we were talking about opposite directions along the curve. Different geometry? Sure. Highly analogous? Oh yeah. Definitely highly analogous, right? Morally equivalent ideas. Just, kind of applied in different circumstances and different details. Okay. All right. So here's what I think is a fabulous way to think about that theorem. It is its own separate accumulation theorem. And so in the same way that, mass accumulates and mass is an integral of mass density, and in the same way that circulation accumulates and therefore is an integral of circulation density, likewise, outward-oriented boundary flux accumulates and is therefore an integral of flux density. Same basic ideas. Right? So I think this is a great way to think about it. I like to think of the Green's theorem and the two-dimensional divergence theorem, these last two theorems I can't quite reach, as being parallel theorems. Or kind of analogous theorems, and rather than thinking as one as a special case of the other. Okay. All right. By the way, just real quick for your possible curiosity, this term, flux density, is extremely common. You're going to hear that a lot. Certainly I did in my physics classes way back when. I would say that in my physics classes, I think I heard the term flux density more than I heard the proper term divergence. Right? It's a very common term. And it's so natural, right? It makes loads of sense. Why do we call it flux density? Because it is literally the density of this stuff called flux. I mean, it could not be more natural. Right? So anyway, heads up, you're going to hear that term, and again, big fan, because again, it speaks to the point. That's how you should think of divergence. And now that said, this term here, not so much. You're probably not going to hear that term circulation density as much, but I don't know why. And I wish that it were in more common usage. It makes loads of sense. It's for totally analogous reasons. Okay. All right. We're a little short on. Okay, I have a minute and a half. Let's see here. I'm going to plant a real quick thought, and then we'll call it a day. And that is the fundamental theorem of calculus. I know y'all know the fundamental theorem of calculus. I'm going to assume that y'all are good with the fundamental theorem of calculus. I just want to point out, you can think of the fundamental theorem of calculus as a way of computing change. Don't think of it as a way to compute integrals. Think of it as a way to compute change. And change is an accumulating quantity. So the fundamental theorem of calculus that you've used a bazillion times previously is just another example of an accumulating quantity that you can view as a stuff that you can therefore compute as an integral. And we'll talk more details about this next time. All right, see y'all later.